And we're live. Yes. Joe, you keep challenging me to all these contests with Smash Brothers. Why don't you go join Mr. SAR's gaming club and play him there? Anywho, welcome back. Believe it or not, we are in the beginning of the third marking period. Unbelievable. It's like the longest, quickest, craziest school year of your lives. It's insane. Anywho, for those of you that are in the live chat right now, as I've been doing, I am simply just going to ask those of you in the live chat to please leave a comment for my records. In fact, I'm going to type that in. Please leave a comment for my records. And I'll put that comment into the chat just in case you haven't already done so. And of course, if you're in my classroom today, then you're all good. Oh, here are all the comments. Oh, people's coming in for the live stream. Excellent. In terms of midterms, I'm trying to finalize what your midterm grades are. Did you all receive my messages? The emails that I sent out? Some people are nodding yes. Okay, good. Yeah, that was a huge blunder on my part, but it may end up working to your advantage if you do play your cards right. The blunder, in case you are wondering, was the fact that when you guys took your midterm, I don't know how or why, it completely slipped my mind that there was an open-ended part that was not on Linkit. So I'm like, why in the world would we give an open-ended part not on whatever? So I sent you all of that important information. Some of you have already gotten it done, and I appreciate that. But I gave you a little time. I emailed you, messaged you on Google Classroom. You have to get that Google form done. Attach whatever work you can to the midterm classroom assignment and get that thing done. Looking at the multiple choice from Linkit, some of you do need to do better on this open-ended part in order to improve your midterm grade. But yeah, if you haven't gotten it done, you need to get it done before 2 o'clock today. I gave you a little extra time to get that thing done, number one. Number two, as I said in the email, I would be grading somewhat more leniently, in a sense. Please get it done if you haven't. Anywho, for all of you wonderful people that are here live with me this morning on the computer and in person, I am going to ask that you have those notebooks out and open. So excitement. Yes, I said that on purpose. We're jumping right back into it because there is no time to waste. Let's see here. For those of you in the Google Classroom, in the online chat, in a few minutes, I am going to be posting a couple of PDFs into the stream. And those PDFs will look something like this. There's a 6.5 and there's a 6.6. But until I do so, I'm going to just very quickly take a moment and give these to those of you that are here today. Make sure. Why can't I separate paper? There we go. Okay. Like I said, for those of you in the live stream, I'm about to post the PDFs of what we're working on to the stream today. Let's see. Add from the drive. Recent. These two. Insert it. PDFs for today. Post it. Come on. Come on. Still says posting. There it goes. It just went through. So if you would, for those of you that are in the live stream, check your Google Classroom stream. Check your Google Classroom stream, and you will see the 2 PDFs that we're going to be working on today. You guys in the classroom can't see it, but Joe is throwing some inappropriate comments at me in the chat. No? Okay, whatever. Those of you in the chat will take care of them. Okay. I'm looking at the 6.5 side. Now, what I want to do is I want to briefly introduce what we're going to be focusing on today. And then I want to throw a bunch of the stuff into our notebooks. Now, a lot of the stuff that we're going to be working on today, some of it is going to be a little bit of a rehash of what we've done. Do you want us to send pictures of those worksheets? No, I don't want you to send me pictures of those worksheets. You have the PDFs. So because clearly this is not easily seeable from the computer screen. So you have the PDF, so you don't have to wonder exactly what this thing is saying. But yeah, anyway, we're going to be working through some of these problems, which are going to be somewhat familiar to you. We've done some of these in the past, and we're going to be expanding upon a lot of the stuff that we've done with radicals. There's some extra information that I have to throw at you. If you look at the back of that worksheet, the 6.6 side of that worksheet, there we go, you will see, again, some additional problems to which we've done things like this in the past. You have a basis of understanding for some of these problems, but I have to expand upon what we've done. There is something big coming up in this chapter. There is something big coming up in this chapter in regards to solving equations. But in order to get to that part, we need to make sure we have this down first, this information, the 6.5, 6.6 information, and then we will be able to apply it to the stuff that we are going to do. Again, just a reminder for those in the chat, I see 11 of you now. If you haven't commented, please make sure that you do. So, for example, looking at the 6.5 side, what I am going to ask you to do, and I'm going to do this in my notes as well. But what I'm going to ask all of you to do is to copy down on the 6.5 side of the worksheet, copy down numbers 1, 2, and 3, leave space for the work that we're going to put in place. But please, please, please write down numbers 1, 2, and 3 into those notebooks. I am going to do the same thing into mine right now. And then we'll see where this thing kind of takes us. Let's see here. There we go. Today is the 29th. There we go. And I'm just going to call this radical expressions. Everything's going to be about radicals for the next chunk of time throughout the rest of this chapter. Technically, we've only gone through half of chapter 6, and we're going to have to build upon that information. So I asked you to write down numbers 1, 2, and 3 as an example, and we're going to go through them one at a time, just to kind of show you where this whole thing is headed. Number 1. I'm looking at number 1, and I'm told to simplify this thing. Simplifying does not mean get a decimal. Simplifying does not mean get me a decimal. It does not want a decimal. You may not know it, but 540 is not a perfect square. Unfortunately, it just isn't. And yes, this is a square root that we are dealing with. Our job is to simplify this thing down as much as humanly possible. There are shortcuts that you can take, but if you don't recognize when those shortcuts actually happen, there is just a simpler way of going through it. And that way of going through it, well, I'm going to need to break this 540 down as much as humanly possible. Come on, calculator. There we go. Click. And no. Click. Plus sign. Boom, boom, boom. There we go. Cleared. 540. Now, clearly, I can divide 540 by 2. Oh, look, I can divide it by 2 again. Oh, I can't do it anymore. I can divide 540 by 2 that many times. Now, again, I'm going to try and break this thing down as much as humanly possible. So, let's see, I got a 2 and a 2 so far. So, hold on, let me write something down here, and then I'm going to show you what I wrote in a little bit. All right, 135. Clearly, 135 is divisible by 5. Can I divide it by 3? Oh, yeah, I can divide it by 3. Divided by 3. Divided by 3. Divided by 3. Sweet. And then I get a 5 left over. Interesting. Here's what I wrote down. Here is what I wrote down. I was able to divide it by 2 twice. I was able to divide it by 3 times. And then there was a simple 5 left over. This is a square root. Now, I wouldn't recommend doing the problem like this all the time. I just think that it's easier to see this example kind of split up. But the only way to escape a square root is if you have the proper exponent. And in this case, you need a perfect square. So I'm going to rewrite the problem one more time after I do this. But I'm going to do this. I'm going to pair together these 2 2s and these 2 3s. Why 2 of them? Because it's a square root. Because it's a square root, I need to pair together 2 of them in order to get them to work properly. The 3 and the 5, sorry, you're out of luck, 3 and 5. Let me rewrite this problem. So I'm going to set this equal to the square root of 4 times 9 times, well, the 3 and the 5, unfortunately, I'm just going to leave them as a 3 and a 5 for now. Although I will change them to a 15 in a little bit. But you should recognize that 4 is a perfect square. And you should recognize that 9 is a perfect square. As a result, this problem becomes the following. Look what I just wrote. I'm going to walk up to the board real quick. When you take that square root of 4, it becomes a 2, but now it is no longer stuck inside of that radical. When you take the square root of 9, it does become this 3, which is no longer inside of that radical. This 3 and this 5, sorry, sucks to be you. You're still stuck inside of that radical. There's one more little step to take, which is to do 6 times the square root of 15. Let me zoom out and kind of show you that full process. And then I want to show you a small shortcut, because some people do like shortcuts to these problems. I see the square root of 540. I break this thing down as much as I possibly can, utilizing my calculator. I could divide it by 2, I could divide it by 3, I could divide it by 5, but how many times? And then I write those numbers out. Because it's a square root, the only way you're escaping a square root is being a perfect square. So I put together 2 of the 2's to make a perfect square. I put together 2 of the 3's to make a perfect square. Sorry, this 3 and this 5, you don't make a perfect square. You're stuck and stuck and stuck inside of that square root. But the 2's and 3's that I put in parentheses, they become a 4 and a 9, a perfect square, which become a 2 and a 3 once you take the square root, which become a 6 when you multiply them together. There is a shortcut you could take. Some people recognize the shortcut, some people don't. If you don't recognize the shortcut, no harm, no foul. You can follow this process and get the thing done. But if you recognize the shortcut, oh man, won't that be great if you could recognize the shortcut? See, the thing is, 540, it's not obvious what you can do with the number 540. 540 is clearly divisible by 9. 540 is clearly divisible by 4. But check this out. 540 is divisible by 36. 540 is, clear that so everyone can, in the chat can see it. It's divisible by 36. Watch this shortcut. And I'm going to be very clear. If you are doing these problems and you recognize the shortcut, by all means, do the shortcut. Shortcut. The square root of 540 is equal to the square root of 36 times 15. 36 is the largest perfect square that you can get out of 540. It is the largest perfect square that you can get out of 540. As a result, well, square root of 36 is just 6, and the 15 is left behind. That cuts out a lot of extra steps. I do not expect that everyone will take the shortcut. I do not expect that. But if you see it, take it. But you got to be sure that it's right. Largest hidden perfect square. Let's take a look at number 2. I also had you write down number 2. This is number 2. Now, oh no, now we're cooking. Is that thing broken? I don't know if it was broken.
I don't think so.
Okay. Yeah. Cube root of negative 432. Now we're cooking here. Now it's a cube root. Now the rules are different. It's the cube root of a negative. Being that it is the cubed root of a negative, you can do that because the cubed root of negative 1 is just negative 1. So I'm going to start with this process. I'm going to take that 432. I'm going to ignore the negative temporarily. I'm going to come back to the negative in a moment. But I'm going to take the 432 straight to my calculator. 432 divided by 2. I did it. Let's do it again. I could do it again. Oh, I can do it again. Okay, how many times have I done it? 1, 2, 3, 4. Okay, only 4 times. So let's see. This is equal to, I'm going to show you what I wrote down in a moment. Okay. Divided by 3, 1, 2, 3. Okay. Okay. So in my calculator, I divided this thing down as much as it could possibly go, and here is what I wrote. Here is what I wrote. The cubed root of negative 432 is equal to the following prime factorization. Notice I put the negative 1 separately. just because I have to deal with that -1. I was able to divide by 2 4 times. And then ultimately, in the end, there was a 27, which that 27 can be broken down 3 times 3 times 3. Now, notice we have a cube root. And because we have a cube root, I need to put together 3 of these numbers to make a perfect cube. Again, you don't always have to do it like this, but I'm just showing you how you can break this thing down. There's always alternate ways of looking at this, but this is just another way. Same thing with these 3s right here. There's 3 of them, which would make a perfect cube, which a perfect cube is allowed to escape a cube root. Now, I just want to point something out here. Go back over here. Look what I'm typing in. The cube root of -1 is -1. This is something that we have to remember. -1 times -1 times -1 is -1. It seems like an arbitrary thing, but you are allowed to take the cubed root of -1, which is just -1. So this -1 by itself is allowed to escape that root. Ultimately becomes -1 times 2 times 3, which I'm going to go up to the board to show you where all these things went. And then it's times this cube root. Move that up a bit. Let me draw a little map up here so you can see where all of these numbers are going. Here we go. These 2's became just a 2 on the outside of the radical because of the cubed root of a cube. The cube root of 8, 2 times 2 times 2. This -1, as we talked about, is allowed to escape because the cube root of -1 is -1. These 3's, which make 27, the cube root of 27 is just 3. That is where they went. And then ultimately, this last 2, unfortunately, had no way of escaping that cube root, so it just stayed behind where it was. It is not allowed to escape. Now, I still have to simplify this a tiny bit more, but this is what I got. Go away, use. -1 times 2 times 3 would get me -6 cube root of 2. -6 cube root of 2. Here's what I want you to do. I want you to do number 3. I'm only going to give you a couple minutes or less. Couple minutes or less. But I want you to attempt to do number 3 on your own. Of course, I will show you what the exact answer is. Keep in mind, there's no one way to do it. The way that I do it may not be the way that you did it, but you would still get an answer. So take the next minute or so. Knock out number 3. Show me what you got, figuratively speaking. While you guys are wrapping those up, just a general question. I don't know what grade it was. It doesn't matter to me what grade it was. Back in the day, you had to know perfect squares. What perfect square did your teacher require that you know up to? Was it like 12 or 15? Like, like your teacher had you like, oh, like 1, 4, 9, 16, 25. They tried to get you to memorize perfect squares. Did they do that? No? Really? Mine did. My teacher back in 5th grade, I went to Collins School. Mrs. Rollman, she retired a very long time ago. She had us memorize up through 12 squared, perfect square numbers. It was incredibly helpful. I went a little bit above and beyond because I'm weird, but I had memorized up through like 15, 16 perfect squares. And then when I got to middle school, I don't know why, I just felt the need to memorize perfect cubes because I'm a weirdo. But knowing your perfect squares is definitely helpful. Knowing your perfect cubes is also helpful. Here's the thing. I'm not going to make you memorize perfect cubes. But you should know some basic ones. You should know that 1 is a perfect cube. You should know that 8 and 27 are perfect cubes. You should know 64 and 125 are perfect cubes. And you should know a very basic perfect cube, a very basic perfect cube that is going to come up in a problem in a little bit, but you should know the number 1,000. 1,000 is a perfect cube. It is 10 cubed. I wouldn't make you memorize all of them, although it could be potentially helpful to be familiar with them. But I digress. Let's take a look at number 3. The cubed root of 128. Now, 128 is not a perfect cube. It is not a perfect cube whatsoever. In fact, if you did know this, okay, I just said a few moments ago how I said I memorized all my perfect cubes, or not all of them, but I memorized a ton of perfect cubes. Would it surprise any of you to know that I've also memorized powers of 2? No? Like 2, 4, 8, 16, 32, 64, 128? Okay, whatever. 128 is 2 to the 7th power. Watch. 1, 2, 3, 4, 5, 6, 7. It's 2 to the 7th power. 2 to the 7th power. 128. Again, it's one of those things that comes in handy. You never know when it'll actually help. Flip. This is really 2 to the 7th power. Or 2 times 2 times 2 times 2 times 2 times 2 times 2. There's 7 of them. That's one way of doing it. Again, there's other ways of doing this problem. You could leave it as 2 to the 7th, but then eventually break it up. In fact, I will show you that alternative way of doing that in a few moments. But since we are working with a cube root, these 2's can escape, and these 2's can escape. That last 2 is out of luck. This becomes 2 times 2, which are the 2's that escaped, times the cubed root of 2, which in reality is just 4 third root 2. That would be the actual simplified way of doing this particular problem. Very strange, but that's what it is. I love problems like this. Here's an alternate way of looking at it. Check this out. I'll show you another way of doing this problem, because I want you to have your options. One way of looking at this problem is rewriting it like this. 3 times or 3 times, the third root of 2 to the 7th. Which the third root of 2 to the 7th could be broken up like this. Making sure people in the chat can see that. In which the cubed root of 2 cubed is just 2. The cubed root of 2 cubed is 2. And the third root remains around that 2 to the 1st, which cannot escape. Gives you the exact same answer. It's just an alternate way of looking at it instead of having to write out all of those 2's. I don't want to write out all of those 2's. I don't feel like writing out all those 2's sometimes. What if it was like 2 to the 12th power? I don't feel like writing it out 12 2's to do this problem. Fine. Stick with the exponents. The exponents can get you there all the same. Okay. I have a math question that I'm uncertain as to what the true answer should be, because I feel like I've heard teachers argue over this question. Let me show you what I'm referring to. I have seen teachers argue over math. In fact, math arguments are amongst my favorite conversations of all time. But I need you all to write down this example. It's not on the paper. We'll go back to the paper in a little bit. The 4th root of 4. This is kind of a debated question as to, well, how do we know whether or not we're done? How do we know that we have the simplified version? How do we know? How do we know? How do we know? You have to dig. You have to learn how to dig mathematically. You have to learn how to get your fingers dirty while digging for the mathematical answer. The 4th root of 4 is a certain decimal that pops up a lot in trigonometry, but that's besides the point. The reason why the 4th root of 4 is somewhat of a debated question is, well, you tell me now. You tell me, how does one break up that big 4? What would you break it up as? 2 times 2, right? You would break it up as 2 times 2. But in order to escape a 4th root, what exponent do you need? What do you need in order to escape a 4th root? Say again? Yeah, you need 4 of them. But you don't have 4 of them. You only have 2 of them. And you could see that right here. Hold on. You could see that right here, where you could break this up as the 4th root of 2 times 2. You don't have enough. Can't do it. Oh, no. That's really windy outside. Back to this. This, unfortunately, doesn't help us. But something else kind of does. Remember the nth root of a to the m power is equal to a to this exponent. Let me zoom in on that. Remember, this is something we did well before midterms. This is something that I introduced to you, goodness gracious, second week in January or some junk like that. I don't know. The concept of power over root. Power over root. knowing this allows us to take that problem that I just wrote up, that example, and do the following. Instead of writing it as 2 times 2, I am going to say that it is equal to the 4th root of 2 squared. Because 2 times 2 is 4. 2 squared is 4. And if I use that exponent in the remember statement, this becomes 2 to the 2/4 power. What do you kind of want to do with that exponent? What do you kind of want to do right here? What do you mean divide? What would you turn it into? A half. Which now, 2 to the 1/2 power, I don't know if you know this, but that's now a square root of 2. This is one of those things in math that people get a little upset at. And it's like, well, what do you mean the method that I did at the beginning didn't work? Well, no, it didn't work. Breaking it up, you can't let that 4, nothing in that 4 can escape. You can't. It's already simplified. Wait, it's already simplified. Okay, I guess we're done. Uh-oh. Let's dig a little bit. If you rewrite it into that fractional exponent, that fractional exponent can simplify to become a 1/2. 2 to the 1/2 is the square root of 2. The reason why this is debated is just because mathematicians are like, well, we need to have one specific set of rules in order to simplify something. Yes, I understand one specific set of rules to simplify something because you want to write an answer as simply as possible. Unfortunately, there's multiple ways. You ever hear the phrase, there's more than one way to skin a cat? You ever hear that phrase? You know how disgusting that phrase is? You ever tried skinning a cat? Thankfully, none of you nodded yes. Just saying. It's a gross phrase. But there's more than one way to do this problem, which is perfectly valid. Perfectly valid. More than one way to do this problem. Have I talked about Tom's River? I haven't? How do you get to Tom's River? What if the Parkway's closed? What if Route 9's closed? Yeah, but you got to know those back roads, right? Will they all get you to the same destination? Yeah, just in different ways. Just in different ways. Some are faster than others. Some are simpler than others. Some are crazier than others. He just said he said helicopter in the chat. So, okay. It would work, you know. Some are more expensive than others. But they'll all get you there. They'll all get you there. But now here's the deal, though. You mentioned the Parkway, and then you mentioned Route 9, and then he said back roads. Would you agree that there are a lot of people in this school that have no idea how to do those back roads? Right? Yeah. So if the Parkway is closed and Route 9 is closed, what do those people do? Maybe that would suck if they had to walk all that way. You know, yeah, maybe pick another day when it's hopefully open. You got to find another way, though. You got to have an alternate method. You got to have a way of getting there. Okay. I'm writing down on that same worksheet, I'm writing down number 11. Please write down in your notebooks number 11. And we'll talk about what we do here. Number 11 the square root of 11 over 9. Oh no, we have a fraction. Check this out. You are totally allowed to do this. You are totally allowed to do that. Why? Because multiplication division allows you to do that. You are allowed to split up a radical by multiplication or division. I'm going to repeat that, but I'm going to repeat it slightly differently. You are allowed to split up a radical only by multiplication division. Because of the properties of multiplication and division, you are totally allowed to do something like that. And the reason why this is vital towards understanding these problems is because now, oh snap, I can take the square root of 9 and just make that into a 3. Yes. Yes, you can. And that is our answer. Isn't that weird? Say it one more time. Yes, you are totally allowed to. Again, justification. The justification behind it is that multiplication division. See, the thing is, and I'm going to write this on in red, and then I'm going to erase it. If this were the square root of 11 plus 9, I can't do it. I cannot do it. I'm not allowed to. I cannot make that the square root of 11 plus the square root of 9. Sorry, no, sucks to be you, can't do it. Because you are only allowed to break those radicals up under multiplication division. It has to do with the distributive property. You are allowed to distribute exponents. If there's multiplication division on the inside, that's the only time you're allowed to. It has to do with that, but yeah, that's the answer. It looks weird, but that's literally all that there is to it. For this problem, that is. For this problem, I want to emphasize this problem, because we're going to face something in a moment that you're not going to like. Anyway. Here is the big problem for today. The big problem for today. Number 12. I need you to write down number 12. This problem is going to be the most important problem that we do today. Number 12. I'm going to spend a bit of time on number 12. The cube root of 216 divided by 24. Question. Very important question. What is the number of the devil? Say it again. Better question. Ready? Why don't you say 666? Does anybody have an answer? Everyone says 666, but nobody says, I don't know that any people who say 666, right? Part of the reason is because there are some people who believe, based on the original Greek translation, it was originally written in Greek, that there are meant to be spaces in between the numbers. There's not really punctuation back in like the original Hebrew, and that was the theory going on with the Greek. There are some people that believe that the actual number of the devil is not 666, but there are some people who believe the actual number of the devil is 216. They believe it's 216. And the reason why they believe that is because, well, since we all say 666, what could go in between them except maybe multiplication symbols? I don't know. Which is weird. Anyway, it's a silly theory. It's a silly theory. It's just one of those things. It's so weird. Everybody just says 666 and they just take it for granted. I don't know. Anyway, back to this. The reason why I bring this up is because look what kind of problem we're dealing with. We are dealing with a cube root. We are dealing with a cube root. And 6 to the third power, it's a perfect cube. So I can take that 216 and I can do something like this. Check this junk out. I could break this thing apart to be the cube root of 216 over the cube root of 8 times 3. Now, I want you to look at that. Oh, Miss Mark, you didn't write 24. I know I didn't write 24 because 24 is not a perfect cube. 24 is not a perfect cube, but the number 8 is. The number 8 is a perfect cube. And because of that, I broke it up preemptively, knowing that it was the largest perfect cube that I could get out of that problem. Watch what happens next, because this is really going to mess with your heads. As I said, let me repeat, this is the most important problem you will see today. This equals 6 over 2 the cubed root of 3. Now, the reason why 6 is on top is because the cubed root of 216 is indeed 6. I just showed you that several different ways. The reason why that 2 is sitting on the bottom is because the cubed root of 8 is 2. And the reason why that cubed root of 3 is just sitting there is because 3 is not a perfect cube. Now, I know exactly what everyone might be thinking in regards to this problem. Why is Mr. Markey talking about this being the most important problem today? Why is he making such a big deal about this problem? This problem seemed quite simple, really. This perfect cube root. Like, look, it's done. Isn't it done? No. This problem is not done. It is not done. It is not simplified. We are not near the answer quite yet. Let me explain. A long time ago, mathematicians came up with a unified way as to how to express answers. For example, watch this. If you are writing out a math test and you get an answer of 2 over 4, do you leave it as 2 over 4? No, because you have been conditioned to take that 2 over 4 and reduce it to a 1/2. Yes, absolutely yes. You simplify it. If you have an answer where it's like the square root of 16, you don't leave it as the square root of 16 because you have been conditioned to take the square root of 16 and make it a 4. Yes, absolutely yes. Because over the years, you have learned all of the rules of simplifying problems. Here's one more. You are not allowed to leave a radical symbol in the bottom of a fraction. Let me repeat that. You are not allowed to leave a radical symbol in the bottom of a fraction, it is not considered simplifying. So we have to do something about it in order to simplify this problem. We have to do something called rationalizing the denominator. Let me write something in my notes here. We have to rationalize the denominator. I say rationalize because we need to turn the denominator into a rational number. This is one of those rules that mathematicians decided upon a very long time ago. They decided, well, technically, in order to simplify these things properly, in order to get everybody to get to the same answer, we need to rationalize the denominator. It's a similar process to how they thought about, well, you got an answer of 2 over 4, you got an answer of 3 over 6, and I got an answer of 12 over 24. Who's right? Well, we're all right. Because you got to simplify it. And when you simplify it, you should all get the same answer. So here's what we have to do. First, I think about what is needed in order to make this radical disappear from the bottom of the fraction. It's a cube root. The only thing that's going to allow me to escape a cube root is if I have a perfect cube. The only way I'm going to escape a cube root is with a perfect cube. So here is what I'm going to do. I'm going to take this 6 over 2 third root of 3, and I'm going to multiply it by a cube root over a cube root. Now, I haven't written anything on the inside just yet. I haven't written anything on the inside of those cube roots just yet. Here's what I am going to write. What the heck are you doing, Mr. Markey? You'll see. You'll see in a moment. Let's agree on a couple things. First, what did I just multiply that fraction by? What did I just multiply by? Say again? Well, 3 times 3 is 9. Is that you're like cube root of 3 times 3 over cube root of 3 times 3? You know what I actually multiplied by? Technically, I multiplied by 1. This fraction by itself, what's anything divided by itself? Is 1. I've multiplied by 1. Remember back in the day, you had to find like common denominators and all that junk? Yeah, like if I added together, if I added together like 1/2 plus 5/6, didn't you back in the day have to multiply that by like 3 over 3 in order to find a common denominator? Same concept. I'm multiplying by 1. And by multiplying by 1, I am not changing the value of the problem. Now, how many 3s do I need to escape a cube root? I only had 1. I needed 2 more. The only way you escape a cube root is if you have a perfect cube. You have 3 of them. I only had 1. I need 2 more in order to do this. Oh, snap. Hold on. Equals. 6, the cube root of 9 over 2, the cubed root of 3 times 3 times 3. I am allowed to do that. I'm allowed to put them back together. Remember you asked me before when I took the fraction? I took the fraction. He's like, you can do that? And I split the fraction up, right? He's like, you can do that? Yes, I can do that. Why? Multiplication, division. Not only am I allowed to take a radical and watch this, split them apart, whether it be by multiplication or by division, I am also allowed to take that radical and put them back together if multiplication, division. Oh, my glasses. My daughter broke my glasses the other day. I'm very sad. They're held together by tape now. See? Oh, there's the tape in my glasses. Anyway. Ultimately, here's what we get. My marker. There it is. 6 cube root of 9 over 2 times 3. Wait a minute. 2 times 3. Yeah, because the cubed root. The cubed root of those 3's just became a 3. Wait a minute, Sparky. 2 times 3 is 6. Yeah, it is. 2 times 3 is 6. But there's a 6 on the top. Yes. Which means that's your final answer. This may be the first day you have ever seen anything like this. We are going to get more practice. I promise you that. In the meantime, I'll see you guys in February, right? Look at that timing. Look at that timing. Anyway, if you haven't left a comment in the chat, please make sure that you do. And yeah, we'll see you then. I'm going to sign off in a moment. I'll just give you a moment to kind of leave the comment if you haven't already. I saw the comments that you guys all left at the top. Come on, watch. Woo! My watch broke. Everything is falling apart on me, dude. Even my soul. See you guys. Have a good one. Click. Click.
Have a good day.
You too.